Hi everyone. This is lecture 2 of module 2, so we're in the chemical oceanography module, and today we'll be talking about the origins of the oceans. So to talk about the origin of the oceans, we have to go way back to the formation of Earth and the solar system. So the most common hypothesis about the origin of Earth is what is referred to as the nebular hypothesis. And so that's the idea that basically everything in the solar system emerged from this nebula, which is this massive cloud of gases and space dust, primarily made of hydrogen and helium, which are the first two elements on the periodic table. And here, I think this image is sort of a cool way to look at it. So you have this massive nebula at the top, which is sort of up here. And it's diffuse, it's huge, it's this gas and space dust and everything, and it starts to contract because of gravity. And it starts to focus material at the center of the cloud, and that's basically where the sun forms in the center here. And so all of this mass starts to get concentrated, and you end up with the sun, and it starts to flatten out and then rotate to form this spinning disk. And you still have lots and lots of material sort of floating around. But what ends up happening as you move down to here is that those little small bodies start to bump into each other. And so you end up with objects what they call accreting. So the material comes together to form the protoplanets. And you end up with, eventually, the formation of the sun causes this solar wind, and it starts to blow away all the gases in between the objects that have formed. And so you end up with these objects, which are now the planets or protoplanets, and all the gas and everything starts to blow away, and you end up with then your solar system. And so that's how proto-Earth would have formed. And of course, I'm summarizing like a massive field of geology and Earth history into 2 PowerPoint slides. But nevertheless, we need to make our way to the ocean. So proto-Earth would have been much larger than Earth today. And it would have been homogeneous, meaning there wouldn't have been the sort of layers that we have through the Earth's surface today. So it just would have been sort of a one ball that was, no difference around any of it. And it would have been constantly bombarded by meteorites. And one of these meteorite bombardments would have been big enough to break off a piece that formed the moon. And we think that this was formed from a collision with a very particularly large asteroid. So at this point, also during proto-Earth, you would have had radioactivity occurring in the Earth's core. And so radioactivity leads to fusion reactions and lots of heat. And the heat would have also been due to the contraction. So this larger than normal Earth would have been shrinking. And the protoplanet starts to shrink, and that also releases heat. And so part of the Earth partially melts because of this heat. And this melting and this high heat leads to things being stratified by density. And this is where we get to what we think of as the more modern Earth, which is the Earth that has a layered system to the inside of it. And so here you guys should be fairly familiar with this image of the solar system today. But let's sort of get to density stratification. So this is much like, it's not that different than what we talked about with water masses, being layering themselves in the water column by density. But in this case, it's sort of rock density. So something with a high density means it's relatively heavy for its size. You can think of if you have like a small box of concrete versus a small box of foam, the concrete has a much higher density. It's a lot heavier for its size. And so early Earth would have experienced this kind of gravitational separation where as things were getting hot and melting and the Earth was contracting, you would have had some really high density materials like iron and nickel, and they would have settled below the lower density materials. And so you have this high density core, and then your lower density materials would have formed these concentric spheres around the core. And so these internal structures, so Earth went from being just one homogeneous ball to being something that has a layering system to it and, an actual internal structure. And you can define this internal structure in 2 ways. You can define it by its chemical composition, or you can define it by its physical properties. So if we first think about the chemical composition of the Earth, And this, I think, is what most people are sort of taught in your basic geography or introductory courses, is that you have the Earth has a crust, it has a mantle, and it has a core. So starting in the middle with the core, you have this high density iron and nickel, really molten hot core in the Earth. And then surrounding that, you have the mantle of the Earth, which is mostly iron and magnesium silicate minerals. And then on the top, you have the crust, which is where we walk around. And it's your low density, mainly silicate minerals. And so you can see the chemical composition of the Earth is defined in this way. And what it's basically doing is it's telling you about the different chemicals that you'll find, right, with their chemical properties. Another way to look through the Earth is to define it by the physical properties. And when you break up the Earth this way, you break it into more components. So now instead of just saying we have a core, you now define that there's an inner core and an outer core. And then you have the mesosphere, the asthenosphere, and the lithosphere. And this is a really cool diagram on the right because it shows you on the left-hand side over here, these are your chemical properties. So you've got your core, your mantle, and your crust. And then on the right-hand side, it defines it by your physical properties. So you can see here, you've got this more rigid inner core, and then your outer core, and then the mesosphere, which is part of the mantle, and the asthenosphere, which is also part of the mantle. And this asthenosphere is really important because this has more of a liquid or plastic like component to it, meaning that things can sort of slide around on top of it. And then you have your lithosphere, which is actually composed of, which is where your crust sits, but also where the very top of the mantle sits. And so your physical properties are defined by how, not necessarily the elements that are in there, but how they respond to pressure and temperature and what their physical properties are, whether they're liquid or rigid or plastic, for example. And so here, this is another way of looking at it. So you've got your inner core, your outer core, your mantle. And then if you zoom in on this top bit, and you look here at the asthenosphere, you've got, this is very, very hot, and it's plastic, which meaning it, and the reason we say plastic and not liquid is that it flows, but it's got a very high viscosity. So think about something like honey. Honey flows, but you would be like, nah, I wouldn't really call it a liquid, right? It's very viscous. And that's sort of what the asthenosphere is like. And so then above that is the lithosphere, which is the more cooler, rigid shell. Thankfully cool, so we don't burn our feet and have to literally play the hot lava game. And the lithosphere includes the crust and a little bit of the upper mantle, and it's about 100 kilometers thick. So you can see the lithosphere is more than just the crust, because this would be the crust here, and this would be the ocean crust here. And so it's also important, I think, to introduce that the continental crust, which is mostly granite, is thicker than the ocean crust, but less dense. And so you can see it's definitely thicker. Even in this diagram, you can see they've drawn this ocean crust very thinly here, which is true. The oceanic crust is mostly basalt, and it's very thin compared to the continental crust, but it's denser, which means when they come together, the continental crust actually floats on top of the oceanic crust. And here, this is a nice little just study table of what the difference is between the oceanic crust and the continental crust. So the ocean crust is quite narrow as compared to the continental crust, but it's a lot denser. So your continental crust will float on top. And because the asthenosphere has this plasticity to it, these crusts can move around. The lithosphere can sort of slide around on top of the asthenosphere. And that becomes important later. Okay, another thing to think about is what we call isostatic adjustment. And so this is thinking about how the Earth's crust moves vertically. And so again, this is because this asthenosphere is a bit plastic, the lithosphere has a bit of buoyancy. So it's not sitting rigid on top of the asthenosphere. And the easiest way to think about this isostatic adjustment is that if you have an empty ship and it's floating in the water, you can see it's riding, it sits sort of a particular height above the water. And then when you go ahead and put a bunch of cargo on this ship, it sinks lower, and so it's displaced this water. And so if you were to take all this cargo off, it would bounce back up to the original position, and that's isostatic adjustment. And this happens to continental crust. So if you have a continent and let's say something really heavy is sitting on it, like a massive ice sheet. The massive ice sheet is acting like the cargo, and it's pushing that crust down. And so if you melt that ice sheet and it slides off the continent, then that continent's going to bounce back up. And so this isostatic adjustment is all about this vertical movement, so the buoyancy of the lithosphere on the asthenosphere. And it also has to do with the fact that the continental crust is less dense and it floats higher than this oceanic crust. And so isostatic rebound happens when these crusts, particularly continental crusts, that used to be weighed down by things like glacier ice, sort of bounce back up as they lose that heavy material on top. Okay, so that's a bit about the Earth and where it came from and what it looks like in its current state. And so before we get to the origin of the oceans, and we're working our way there, we have one slide on the origin of the Earth's atmosphere, which we'll have a whole lecture on when we get to the atmospheric section. But it's important, it's a key step in getting to the Earth's early ocean. So while all this density stratification was happening, and everything, the Earth's sort of core and mantle and all that was organizing itself, any gases that were throughout started outgassing. So as you have these materials and you heat them and they density stratify, the gases start to just form and come to the surface. And a lot of what was in this outgassing was a lot of water vapor, carbon dioxide, hydrogen, and then some other things. And this is what would have been made up Earth's early atmosphere, which is massively different from today. Not that these things don't exist in the Earth's atmosphere, but in very different concentrations and in different forms. So essentially, all that outgassed water vapor, over time, as the planet's atmosphere started to cool, that water vapor turned to rain, turned to liquid water. And basically it rained and rained and rained for a really, 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 really long time and filled up that thin oceanic crust as compared to the continental crust, basically made like a basin. So you had these parts of this basically like a bowl that was being filled up with water as it rained and rained and rained and rained and rained. And so from the geologic evidence we have, the first permanent ocean formed about 4 billion years ago. And so the ocean as we have it now has been around for a very long time. And the ocean would have been had relatively similar salinity to today, from the fact that the salinity comes from the rock elements on land. So the continental crust hasn't changed that much. So as the rain's falling over this continental crust, it's dissolving some of it and those elements are going into the ocean. And that's where we end up with having these salts and the dissolved constituents in the ocean. So here you have this in a more of a visual form. So you would have had lots and lots of volcanic activity during early Earth, and this would have released water vapor amongst other things. And then you would have had just massive cloud cover. And then as things cooled, these clouds all started to rain, and it accumulated in the low areas and eventually formed the oceans. So a couple of other things about early Earth and early oceans. The earliest known life forms from the geological record are about 3.5 billion year old rocks, ocean rocks that have bacteria fossilized in them. And it's believed that these are the building blocks for early life on Earth, as it's the sort of most direct evidence we have of life on Earth from 3.5 billion years ago. But it's very difficult to have direct evidence of early Earth's environment, right? Everything has to be done by what we call a proxy. And so when we talk about Earth's atmosphere, the origin of the atmosphere, we'll actually talk a lot more about potential origins of life. But the other thing I wanted to get into with the origins of the ocean discussion today is evidence for continental drift, because this is another key part of understanding the formation of the ocean basins. So at some point, a long time ago, some old dead white guy proposed Pangaea, that basically once they started mapping the continents and people started seeing what the continents looked like, somebody had the idea that they looked like puzzle pieces and that you could put them together. And so this idea of Pangaea, that one large continent existed a long time ago, was proposed. And of course, if you smush all the continents together, then you end up with one large ocean. And this was known as Panthalassa. Pan meaning sort of all and everything, and Gea meaning earth, and Thalassa meaning sea. And then for some reason, don't ask me why, they considered this Tethys Sea to be separate. And so this was widely ridiculed as being absolutely crazy for a very long time. But people started looking for evidence. And what was actually found was, okay, so if you look at the continents, they sort of fit together. But what turns out is that they don't fit perfectly. But if you remember from bathymetry, all of these continents have a continental shelf, right? Before things sort of drop off. And if you take from the edge of the continental shelves and put the continents together, they actually fit really well. And this was done from in the 1960s with some of the first computer models. And what they found was that, from a continental shelf perspective, the continents fit really well together, even better than if you just use the continents themselves. And there's a lot of different lines of evidence for continental drift. So one being that, okay, well, if the continents were together, then you would expect some mountain ranges and things on each of the continents to match up. And that indeed is true. So in the US here on the left, we've got the Appalachian Mountains. It's a mountain chain that runs down the east coast of the US. And in Northern Europe, you've got the Caledonian Mountains. And when you fit the continents together, the way that they appear to fit nicely, you can see that this actually becomes one long mountain range. And indeed, when you look at the rocks on these mountains, they're very similar in terms of their type, their age, and their structure. So that's the sort of type of evidence that you look for explaining how the continents used to be positioned. Another line of evidence is the glaciation. So if you look here at the top with Pangaea, there's parts of these southern South America and Africa and India and Australia that would have essentially been attached to Antarctica and would have sat at a much lower latitude than they do now. And so you would expect to maybe see evidence of ice on these continents. And indeed, when you look at these continents, you see lots of evidence of glaciation, and you can even see the direction of glacial flow. That's what these arrows are showing, that it makes sense that the direction of glacial flow is in line with what you'd expect if they had all been sort of fit together. And that when glaciers move, they sort of they scrape rocks in a very particular way. And indeed, you see that evidence in these various regions. And you also see types of plants and animals that indicate that they would have lived in a very different climate, a much cooler climate. Another line of evidence, getting into fossils, is you might expect if continents were connected that they'd have similar fossils, because obviously the animals would have been roaming around the same places. And indeed, you can see this is one example where in South America and Africa, the only place on the globe where you find fossils of Mesosaurus, which is an aquatic reptile, are in South America and Africa. And so this sort of brings a couple of possibilities, right? They evolved completely independently to be identical in these two different places. Or Mesosaurus at some point swam across the southern Atlantic Ocean, which is sort of difficult to imagine. Or that the two continents were together and that this was just their habitat, was this, this region, which is the most likely explanation. But the real sort of nail in the coffin for continental drift was about seafloor spreading. So saying that there's evidence for it is different than saying you can explain how and why it's happening. And so World War II was actually really instrumental in improving our understanding of the continents, because what happened is, if you remember during the bathymetry lecture, we talked about how a lot of these ships and submarines were using sound waves and radar and sonar to sort of look for one another. And there were quite a few people, Harry Hess included, who's most well known for it. Some people who were in the military were also were scientists. And so instead of just leaving the equipment on every once in a while, they would leave it on all the time and basically trying to generate lots and lots of data. And so one of the things they found was evidence for seafloor spreading, and these mantle convection cells, which we'll talk about. And I know we already talked about this a bit with bathymetry, but now it's kind of related to more about setting up the structure of the current ocean. And so what the idea is for the original ideas for plate tectonics was that because the asthenosphere is plastic and there's these convection cells and it's hot and everything's moving, that you would in some places have this hot molten rock come to the surface. And that this is actually this mid-ocean ridge, this mountain range, is where you're forming new crust. And so you're forming new continental, in this case, new oceanic crust on the Earth's surface. But in order for there to be new crust, it means you have to be getting rid of crust somewhere else. And so the idea is that you create the mid-ocean ridge and that this crust is actually moving this way and this way. It's spreading. And eventually, this oceanic crust goes down, because remember, it's more dense than the continental crust, and it subducts underneath some of this other crust here. And you end up with these deep ocean trenches and things like these volcanic arcs. And so the mid-ocean ridge is that spreading center where you're moving the crusts around. And you also create these subduction zones where you're destroying crust and these deep ocean trenches. And so this was an idea that, so there's a couple of implications of this idea. First off, it means that the oceanic crust is constantly being generated new and being created and destroyed. But there's also this idea that you can record this process in seafloor stripes that are recording Earth's magnetic polarity. And this is kind of cool. So this is an image that shows this. So Earth's magnetic field, every once in a while, goes through a reversal. And I'm not going to get into the sort of details of why this is. This is more of a sort of geology issue. But suffice it to say that you have a normal magnetic field. And so as lava's erupting and you're forming new crust, there's rocks called magnetite that are in the crust. And those magnetite crystals align themselves with Earth's magnetic field. So you can actually go and look at this rock, and you can see that the crystals are all aligned according to the magnetic field. Now, what's interesting is as this crust, this green crust here that was formed, moves away and you get new crust, if there's a reversal of Earth's magnetic field, which we know has happened, you would expect to see that in this new crust. So now your magnetite's going to be aligned in the other way, right? And so this would give you a sense, if you know something about when the Earth's magnetic rotation happened, went from sort of normal to backwards and back again, then you should be able to see this. And indeed, when scientists look at the crust as you move away from the mid-Atlantic ridge, you see this exact kind of magnetic striping that you would expect. And it aligns perfectly with when Earth's magnetic field was reversing itself. So the other implication of this is about the age of the ocean floor. So remember I said the ocean has been around for about 4 billion years. But in the late 1960s, one of the other things that happened, post-World War II, of course, was that deep-sea drilling was started. And so once you started drilling these rocks on the ocean's floor, you could date them, radiometric dating, and identify how old they are. And the oldest ocean floor that's been found so far is only 180 million years old. But of course, the water is 4 billion years old. And this is really interesting. So it means basically that the ocean floor is constantly regenerating and then disappearing and regenerating and disappearing. So even though the water itself has been around for 4 billion years, that the ocean's floor looks completely different now than it did 4 billion years ago, right? Because it has this sort of age restriction on it. And indeed, when you date the rocks on the ocean floor, you can see this is quite a cool image here. And I think it's easiest to start in the Atlantic Ocean because it's the most straightforward. That right above the mid-Atlantic ridge, which is basically where this dark red stripe is, the rocks are about 0 to 2 million years old. And as you move away from the Atlantic ridge, the rocks get older and older. You can see they move through. They go from 2 to 5 million years old, 5 to 24, all the way up till, they're quite old at the edges here. And right as they subduct underneath the continent, they're about 208 million years old at the maximum. And then they go back, everything goes underneath and gets convected and then starts all over again, where it starts to come back up as new rock. The other basins are just a little bit less straightforward because there's all sorts of other geological things happening. But for the most part, the age of the ocean floor aligns very nicely with this idea of continental drift. And so lastly, just to introduce this idea of the Wilson cycle, which is something you hear about quite often when you think about super long timescale cycles, is a model, a nice sort of general model of plate tectonics that shows the life cycle of ocean basins. So thinking about what the ocean basin is formed, and then it grows, and then it's destroyed. And this sort of table diagram here, I think, shows it quite nicely and gives you some ideas of where this is happening in the modern ocean, which is kind of interesting, and how these different stages of oceanic basins are labeled. So I just wanted to introduce you guys to this so you could take a look at it. It's kind of interesting. And so, of course, lots and lots of stuff about the past, but this is still happening, right? This isn't a past phenomenon. And it will keep happening as long as we have this molten center of the Earth and plate tectonics and volcanic activity. So if you assume the same direction and rate of plate motion from now into the future, eventually the Atlantic Ocean will get bigger, right? Because everything there is separating. And it will eventually start to push the continents away from the mid-Atlantic ridge. So the Pacific Ocean will start to shrink. You'll open up a new sea from the East African rift valleys. The Himalayas will get bigger, and North and South America will move away from one another. And you'll end up with the west coast of the US, California, starting to push up and into Alaska. And you can see this is a world map made by computer models using all that information and looking 50 million years into the future. So you can sort of see what's happening. So North America is moving up and spinning around a little bit because of this Pacific plate. The South American plate is pushing South America over. Southern Africa starts to move, sort of rip apart from Northern Africa a little bit. The East Africa is completely gone at this point, moving on, which is why you're creating a new sea in here. And it's just sort of cool to, think about what things look like in the future.